So zircon, it's the formula. Well, it has zirconium, right? Zr. It has silica and oxygen, so it's a silicate. It's another silicate. Who knew? Who even knew? It's a tetragonal silicate specifically. It has a hardness of about 7.5. Remember, the most hardness scales from 1 being a talc, to 10, 10 being diamond. The specific gravity is a lot higher than zoisite at 4.68. And zirconium itself is actually a pretty large atom, pretty large cation. That's what this is in this particular formula, right? It's positively charged, and it's pretty big, so it can actually contain a lot of unusual other elements as replacements for it, like uranium and thorium and hafnium and a lot of the rare earth elements. Lead, I think, can also be one as well, and that's I think that's because uranium is radioactive and decays into lead, not because I think lead itself replaces. I think it's actually because the radioactive decay of uranium then leaves lead in the crystal lattice. Additionally, because things like uranium and thorium can replace the zirconium in this mineral, you can get what's called metaminced. The mineral can become very, very it's not unstable, because that refers to basically weathering. It becomes really, I forgot the exact definition of metaminced. Metaminced. Amorphous. Oh yeah. So disruption of the crystal structure by radiation from contained or nearby radioactive atoms. Basically, it's. I didn't see it being called amorphous anywhere, so just scratch that. That none of the literature I read said anything about it being amorphous, but it does definitely disrupt the crystalline structure. It actually does. Zircon has a continuous solid solution series between hafnium and zircon. Hafnium is the same, basically the same mineral, but instead of zirconium has hafnium. Literally, that's it. Literally. So that is what hafnium looks like. Whoa, that's cool. Oh gosh, I really wish that of course, Weinrich Minerals, they have such nice minerals. So yes, HFSiO4, or red, orange, brown, yellow, colorless, whereas zircon can be very, very brownish red as well, but is oftentimes kind of gray. So again, it does form a complete solid solution series. Do you guys know what that means? Do you remember what that means? I'm waiting for anybody. That's okay. That's okay. I will teach you. I will teach you the things. So you can imagine that zircon, right? This mineral, zircon. In fact, let me blow this up. So basically, you see that there's zircon here, right? So you can imagine that there is, in this formula, a pure variety will have 100% zircon relative to any other cation, not relative to the SiO4. But just pretend for a minute that the cation spot, because this is the cation spot and this is the anion, right? SiO4 is negatively charged. Zirconium is positively charged, and together they're neutral, right? Zircon can again be replaced with hafnium, which is HF, right? But did you know that you could then potentially have 50% hafnium and 50% zircon or zirconium in the same mineral? Because it's a solid solution series. You could have 20 to 70, 20, 80, 30, 70, 40, 60. It doesn't matter. What the point is that all the way from zircon to hafnium, there is actually different minerals that form. Does that make sense? I'm trying to figure out another way to explain this. So you can imagine, let's say there's 100 balls of zircon, right? And there's 100 of the SiO4. We'll just ignore the SiO4 ones. We're just going to push them away for a moment, right? And there's 100 of them. Well, all of a sudden, these hafnium balls start pushing out the zirconium balls. Okay? 10 of us, and now 10 of you are gone, and now there's only 90 of the zirconium balls left. Well, it can keep happening, and vice versa. You can have more zirconium in this one, too. Does that kind of make sense? I'm trying to think of different analogies that might work here. It's just like trace amounts of things. So instead of the zircon, because zirconium, Zr, can be replaced by uranium and thorium and hafnium, but you can get a ton of hafnium such that you actually get the mineral hafnium instead of zircon. But yeah, there's the same amount of silica and oxygen per zirconium as there are here. There's the same amount of silica and oxygen per hafnium here. So that's what the complete solid solution series means, that you can have hafnium replace or replace the zirconium, and you can have the zirconium replace the hafnium in hafnium, right? I think that stuff's cool. That stuff is what tickles my fancy. I think it's really interesting where you have various replacements of things and trace elements that cause color changes or even mineral changes entirely in some cases. I think it's very, very interesting. There are actually over 50 elements that will replace zirconium in zircon. So the ZR. There's a ton of them. It won't replace them fully. The only one that does that is hafnium. That's the only solid solution series that exists between these two. But that being said, there's a lot of other elements that can replace zircon in trace amounts, such that you can have various hues of color that change. Oh, is that some zoning? I think that's some zoning. God, that's pretty. That's actually a unusually euhedral grain. Maybe subhedral. Rare earth elements, lead, of course, because uranium decays into lead, thorium. And then, of course, because uranium and thorium can replace zircon, or zirconium, rather, it's exceptionally useful for dating the earth and other rocks, especially Precambrian ones and older. It's great. It's great to do with that because uranium decays, so we can use it in radiometric dating. I've actually done a little bit of zircon picking, and these are little tiny grains. They do not look big like this. They look very, 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 very tiny. Apatite and zircon I had to pick, and you have a binoc scope, and you look down, and it's just lit, right? There's no cross polarization happening, and you've got a little petri dish with a bit of alcohol soaking the grain so they don't fly out and they don't just they've got some solution to sit in. And then you take these little tweezers, and then you have to find the best of the best looking grains, because those are the ones that are going to be the best for age dating things. So this would have actually been a decent grain to pick looking at it. I'm sorry, zircon is used to coat the inside of nuclear reactors as well. Twinning, again, is not common in this one, just like zoisite, but it can happen and has been reported. It's just not common. Typically, it's really hard to see zircon in hand sample. You can, but they're typically very tiny little minerals. There was one piece of literature that said something about some amount of pounds heavy piece of zircon, and I have yet to try to find that. I don't know that I believe it, but it may be real. I don't think it is. That being said, most of them are very, very, very small. You do need a microscope or something to see them, but they are oftentimes doubly terminated, and by that I mean they have two. It's called dipyramidal terminations, so both ends look like little pyramids. Basically, they're four-sided. If you look down the c-axis, euhedral overgrowths and anhedral cores are very common, and by that I mean you get like let's say you have a zircon grain floating around in the environment, and it chips or it's bombarded by radiation and becomes metaminked and a little bit broken up and whatnot. And zircons are one of those amazing minerals that actually can become recycled through all of the rock cycle and still exist. They have a really high melting temperature, and they can actually, the older core of the zircon can recycle through nature, right? And then eventually you can have new rings of zircon growing on the old core. And it's so cool. So this is the little zircon that I found. And you can see that these different bands in there are likely because they're different trace elements that are replacing the zirconium that are more dense than the zirconium itself, which is why they're brighter. The darker the material, the less dense it is. I had to turn the brightness and the contrast crazy high to see the zoning in this grain of zircon, because it's just such a zirconium is just so much higher on the periodic table than most of the elements that I would see. The minerals are subadamantine, or the zircon is subadamantine. It can be greasy if it's metaminked, but otherwise the colors include gray, yellowish, reddish, brown, and you can see some of that yellow here in the zoning. And this is that gray look that it it can have, although it's actually very, very pretty. When I think of zircon, typically I see this in my mind, or this from having picked zircon grains all the time. Zircon can be weakly pleochroic, so that means, again, pleochroism is when you rotate the mineral and it's a slightly different color in one axis than the other. This fractures conchoidally, so like quartz, like glass. In fact, you can see a little bit of that rounded fractured surface on the bottom, especially a little bit up here. But that means it's going to fracture like obsidian or glass or quartz. It's going to have those really rounded, convex, concave structures or features. There's concentric color zoning, like we see here. We see the various colors that are displayed in this image anyway. It doesn't really have any decent cleavage. It has 2 poor cleavage planes, and brittle tenacity and conchoidal fracture. I don't know why people would want this for jewelry. It's very pretty though. It mimics diamonds in some cases, and I'll get to that in a moment. It's an exceptionally stable mineral, and that's why I found it in the sedimentary rock at 8,500 feet deep in my samples, which I showed you just a bit ago. It's a source of metals used in industrial materials, so zirconium, for example, like lining of the nuclear reactors, for example. Zircon is ironically most commonly mined in placer deposits, so loose sediment, most likely beaches. Sri Lanka is one of those examples. There are a bunch of areas there that are mined, and it's all loose sediment. Placer mining would include gold panning in rivers and things. This mineral is actually rarely seen in hand sample. It is. You can find it, but it's expensive. It's used in things like refractory bricks and foundry sand as well. Australia, South Africa, and the U.S. are the best places to apparently obtain this, at least in big quantities. They're used in as gemstones too, and this is also used to make cubic zirconia. The refractive index is actually very high. It's 1.93 to 1.98. Anything over 2 is typically metallic. It's been intentionally and mistakenly sold as diamond. And zircon has double refraction, so facets will appear doubly, just like the guy explained with I don't remember. I think it was forsterite. So if you're looking at this and you think you're being sold a diamond, because yes, they do have clear varieties, just peer through it to the facets, and the facets will appear doubled, and you'll know it's not diamond, because diamond doesn't do that. It doesn't have double refraction. It has a very high melting point, like I mentioned earlier, which is why it can be used in things like ceramics and foundry sand. It's so useful. It comes from the Arabic word zargan, which means gold color. It's an ancient, I guess, Arabic word, I think. It's been mined for over 2,000 years in Sri Lanka. This mineral's been mined for ages. For ages. It's often heat treated. They get brown samples and they turn turn blue or colorless when they're heat treated. And if they're heat treated in the presence of oxygen, then they get that gold yellow color. It's Zargon with a Z.